Okay. Well, thanks for inviting me to give a talk today. It's been good meeting you all and seeing old faces. I've gotten lots of technical questions that I can't answer, so I will preface this by saying that I'm sort of new to the pegmatite game, but it's been a real interesting research project so far. So I'm going to focus on some pegmatites in the Northern Appalachians. And really we're thinking about the models of origination. And this is really driven by the fact that everyone's talking about lithium. Okay. But I also want to acknowledge all the colleagues and collaborators that are participating in this research, from USGS collaborators, collaborators up at the Mine, Mineral and Gem Museum, as well as some emeritus USGS folks, Columbia University, American Museum of Natural History, and the Maine Geological Survey. This is a picture actually from the Maine Mineral and Gem Museum. If you have not been there, it's a pretty fantastic museum. It's actually built on top of a research lab from, I don't know if you know Skip Simmons, his research group from New Orleans moved up there, and they brought their instruments there too. So it's a pretty cool place. They also have, I think, one of the biggest meteorite collections in the world, at least lunar and Martian meteorites. Yeah. I also need to acknowledge the funding sources. It's mainly funded by the Mineral Resources Program at the USGS. We have a project that is specifically geared towards developing new methods in isotope studies related to critical minerals. And so the task I'm on, this is something we've been working on. How do we directly date ore minerals or ore related minerals? So we call it beyond zircon because zircon is such a ubiquitous geochronometer. And so I'll talk a little bit about that and how it applies to this project. The Maine Geological Survey also helped fund this project. They've been mapping in the region, which is shown in this little orange area here. And they are now working with the USGS Earth Mapping Resources Initiative, or Earth MRI. And for those of you not familiar with that, it is its own line item on our budget. And it's funding lots of new geophysical surveys throughout the US. And that's part of it. Is also funding state geologic surveys to do mapping and geochemical reconnaissance mapping. And so it's pumped a lot of money into surveys. Some surveys are sort of struggling because it's given them so much work to do. The main survey is not a huge survey, and luckily they have some great emeritus USGS folks up there, as well as several good academic collaborators, which I'll talk about later. I'm not going to talk about the outline, but I thought I should put it up there. But basically, I just want to talk about sort of the history of the area, the methods we're using to solve some of these geochronologic problems related to pegmatites, and think about the processes related to the formation. As I mentioned, lithium is a big driver in a lot of the research that we're doing now, as well as this idea of critical elements and critical minerals. Pegmatites, specifically rare metal rich pegmatites, are major contributors to production. They still make up somewhere over 25% of the production of the world's lithium, and 100% of the cesium and tantalum production. And they are host to a slew of other critical elements and rare earths. So just sort of a way to think about this in hopefully the most simple way. We have common pegmatites, which we see all over the place, typically rich in quartz and feldspar and micas. And then we have the rare elements. And there's two classes that I'm going to talk about today. The lithium, cesium, tantalum, or LCT pegmatites, which are enriched in lithium, cesium, tantalum, as well as beryllium and rubidium and several other elements. And then the niobium, yttrium, fluorine pegmatites, or they refer to them as NYF pegmatites. which are also enriched in titanium, rare earths, zirconium, thorium, uranium. The LCT pegmatites are typically associated with paraluminous granitic bodies. And I say, or not at all. One of the problems we're dealing with in Maine is that we can't find the host bodies to these pegmatites. And then we've also looked at some NYF pegmatites just across the border in New Hampshire. And these appear to be associated with magmatic bodies clearly. So there's really sort of two main hypotheses about granite pegmatite formation. There's the extreme fractionation model, and then there's the anatexis model. And so the picture shown here explains the extreme fractionation, where you have a host body, and as you move further away from the host body, these pegmatites become more rare element enriched. The anatexis would suggest melting from a sedimentary source that was enriched. The third point I show here is something that Dwight Bradley, one of the collaborators on this project, postulated, is that you can form, or a mechanism to enrich and form rare metal rich pegmatites is to have an active tectonic area associated with a salar. So super deep circulation of enriched brines. We'll talk about that a little bit later. So just to give sort of an introduction to the region, this is Maine, obviously. I'm not going to get too much into the geology because it's relatively complex, and I don't think I need to talk too much about it for this story. I'll try to keep it pretty basic. But one of the more famous pegmatite bodies, the Plumbago North Pegmatite area, is shown here in western central Maine. It has a rich history dating back to the late 1800s. These are probably more well known for their gem quality minerals than anything. There was economic mining happening in the region that ended in the 60s or 70s. Since then and leading up to them, there were several significant super rich, very high quality gem discoveries. The name Newry is associated with certain types of tourmaline. Several pockets were discovered. The mining sort of happened on the scale of humans. There wasn't a lot of mechanical mining taking place. There was a little bit of blasting. And so the discoveries are all small, and they all happen in a pretty confined area. One of the best pockets that was discovered, I think, in the 1972, it yielded a 28 centimeter tall watermelon tourmaline that's in the Smithsonian now. This is called the Jolly Green Giant. And the gem mining persisted through the 70s, the mid 70s. It kind of the property was sold. It got sold a bunch of times. Not much has happened since, except for, any of us can go to these. Well, not all of them, but we can go and collect sort of for fun. The Dutton Gem Quarry just produced a tremendous amount of gem quality minerals, including these pretty spectacular watermelon tourmaline. It was it's so famous that other tourmaline mines have tried to say that they're Newry tourmalines, but these have very specific properties that you can suss that out. All right, so modern mining in western Maine. So probably the biggest thing to happen in the area is this new discovery in the Newry area. This is the Plumbago North. It's about 1.5 kilometers away from the really spectacular gem deposit. These are quartz, albite, muscovite, spodumene rich pegmatites. They're unzoned. These are they're spodumene up to 11 meters in length here. And not only that, it has a really high with Li2O weight percent. This basically puts it in one of the top 10 lithium pegmatite deposits in the world. And this was recently discovered. And so, you know, there are still discoveries to be made, but you can see this this figure here that shows where it fits relative to other major pegmatite mines in the world. Okay, so it's been shown, or it's been speculated to be worth about $1.5 billion. The problem is it's in Maine. Okay, Maine has probably the most restrictive metal mining laws in the country. So the 2017 Maine metallic mining laws, and it's sort of in response to several mines in Maine that have acid mine drainage problems. The best example is the Brooksville copper and zinc mine that started in the late 60s. They drained a coastal estuary to do the mining. Once it filled back in, they have consistent acid mine drainage issues. I think 2013, it became a Superfund site. Okay, so the mining laws are no mining in or under, you know, lands of environmental sensitivity, no open pit mines greater than 3 acres, no mines that require treatment of toxic wastewater in perpetuity, including holding ponds. And so there's basically no active metal mining in Maine. And so I think the new Congress there is actually taking, or they're trying to better define these laws. They're not as specific as, you know, there's probably wiggle room to it. So the argument is that this is more like mining like granite dimension stone than mining a sulfur arsenic rich mine or a base metal mine. All right, I just wanted to remind you of this formation hypothesis, and it's important for understanding the process for forming LCT pegmatites. So the Appalachians has a pegmatite belt that goes all the way to the southernmost Appalachians, going from Alabama through the southern and central Appalachians, all the way up into the northern US Appalachians. As you can see here, it seems like there's a higher density in the northern Appalachians, and that's probably for good reason. This diagram is detailed. Oops, sorry. I stole a slide from my SEG talk. Okay, so this is what we know about the timing of and the ages of the pegmatites from the southern Appalachians to the north. And I don't want to go through all the details here, but these have been determined by different geochronological methods, including argon-argon dating, zircon dating by various methods, monazite, columbite dating, and et cetera. Several of them, you'll notice that they have arrows, and that's basically, you know, giving upper and lower limits, so not well constrained.
What's the scale on those ages?
So this is 220 MA to 390 MA. Previous mineralogists and geologists that studied these pegmatites, especially in Maine, did a pretty standout job in describing them and differentiating them into different series. And this is important later on when I talk about the geochronology results. In pink here, I've shown 2 of the Appalachian orogenies that occurred during this time frame. We have the Neo-Acadian and the Alleghenian. I should have pointed out before that there are multiple orogenic events in the Appalachians that span most of the Paleozoic. The big ones being the Taconic and the Acadian, which are older than these, but don't have any clear relationships to the pegmatites. My point here is that the geochronology is not very well constrained on these pegmatite bodies. This is a generalized tectonic map of the area. On the left, it's more of a terrain map, and on the right is a shows a lot of the igneous bodies. The region of most of these pegmatites in Maine is in this area here. There's a large plutonic body here that is Pennsylvanian to Permian in age. Most of the pegmatites, which are shown in purple, these are the purple are the LCT, the blue are the NYF pegmatites. They are associated with metasedimentary rocks for the most part, but proximal to igneous bodies. So there's been a lot of mapping in the area, dating back to the 60s and earlier. And that has evolved through time. There was a big beryllium project that the USGS was running, which led to lots of detailed mapping in the region. So we do have some good base information about the geology of the region. Now with the new Earth MRI funding, there is more detailed mapping, which includes more geochemistry, more geochronology. I don't need you to get lost in the details here, and so I'm trying to simplify it here. But this dark gray body here is a intermediate plutonic body, and in red are the mapped LCT pegmatites. The common pegmatites are shown in light blue, and there's a few Schurl pegmatites here. The mapping actually led to discovery of a new LCT pegmatite as well. And so we've been looking at structural controls, relationships to igneous bodies. Looking at the map pattern, the easy conclusion would be to say this is a igneous body related to or responsible for the pegmatites in the region. This is a cross section. This purple is that igneous body that we were showing, and the pegmatites sort of sit nested in here, but are actually sitting in packages of metasedimentary rocks. Again, I'm not going to ruin the punchline, so I'm just sort of setting this up. The other thing I want to show here is this sort of explains the tectonic or the geodynamic timing of things in the region. These are compilations of dated igneous rocks and detrital zircons that Dwight Bradley pulled together. And I would say you can see, but you can't see. This is the tectonic orogeny. So sort of in the range of about 460 to 480 MA. The Acadian orogeny is the second pink stripe. And then we have the Neo-Acadian and the Alleghenian orogeny. So these are, at least 4 different orogenic events related to the tectonic setting in the region. These histograms show when we have the most igneous activity or tectonic activity. And so I want to show the relationship of those ages to the pegmatites. Well, we didn't have good controls on the pegmatites, so we can't understand how they formed until we know when they formed. And so we are applying new geochronology methods to help understand the process here. And so this is just a picture of the lab in Denver. This is what we call the plasma lab. And it has 3 mass spectrometers and 2 laser systems. So we use laser ablation mass spectrometry to measure isotopes to determine the ages of rocks as well as isotope transfers. And so the instrument we use for these studies is this Teledyne laser here attached to what we call a single collector mass spectrometer. As I said before, we date several different mineral phases. Zircon's the most common one, but we also date minerals like monazite, apatite, which are found in most of the rocks we look at. We can also measure radiogenic isotopes like lutetium, hafnium, barium, neodymium, and lead. And as I said before, we are being pushed to develop new methods of geochronology. So we look at minerals like rutile, titanite, apatite, monazite. These are all related to ore deposits. Some of the newer methods we're developing is dating tungsten minerals like scheelite and wolframite, columbite, tantalite, as ore minerals from niobium and tantalite. We also have already developed the method of dating cassiterite, which is the main tin ore mineral. And so basically the process is we collect samples, we will grind them up or pluck minerals or make thin sections. Typically we put them into grain mounts and we image our grain mounts under SCM. We can use cathodoluminescence imaging or backscatter imaging to characterize the samples before we analyze them. And then once we have all that done, we put the sample into a cell, which the laser ablates. The material that's ablated gets sucked into an ion source where it's ionized, and then we measure the different isotopes in the mass spectrometer. So cassiterite is the main tool we use right now for dating LCT pegmatites because it's a minor mineral, but it's common in a lot of these minerals. And cassiterite has some really nice, unique properties that make it useful for dating these ore minerals. It's part of the rutile group. Again, it's the primary ore mineral of tin, and it's responsible for the Bronze Age. When it got alloyed to copper, that's what makes bronze. There is a lot of information stored in cassiterite. We can see growth banding on the left is a cathodoluminescence image of a cassiterite crystal. There are dark and light bands. We can make we can postulate some things about the zoning just by looking at it. The darker bands are usually higher in iron. Some cassiterite has no obvious banding because the iron quenches the Cl. We can look at we can make maps of other elements too, just to see what's happening as this cassiterite is forming. But these are just several examples of different cassiterite crystals we looked at. The values on here are uranium concentrations, and so they're relatively low. For zircon, we like to see hundreds of parts per million uranium to get good data. Typically, cassiterite is an order of magnitude lower than that, so we have to use bigger spot sizes to sample more material when we're ablating it. So for zircon, our spot sizes are about 20 to 25 microns. For cassiterite, we go up to about 135 micron spot size. Luckily, most of cassiterite we find are they get large. So we can put, 100 spots on a grain if we really want to. So it has a moderate uranium concentration. It has very little common lead. And so if you know anything about geochronology, the idea, at least for uranium lead, is that the crystal starts out with no lead in it, and all the lead that accumulates is from the decay of uranium. If you have lead in the crystal already, it makes the calculations more difficult. However, in this instance, if you have variable amounts of common lead, you can use that to your advantage, and I'll show you that. The other really good thing about cassiterite is it has very low thorium. Okay? It has the thorium-uranium ratio is very, very low. Once I get to the next slide, I'll show you why that's important. Also, cassiterite persists in the geologic record for very long times. It's very difficult to dissolve cassiterite. That's why it hasn't been used a lot as a geochronometer. Prior to in situ methods like laser ablation, you would dissolve your crystals and isolate uranium and lead and measure those ratios. It wasn't until recently that people figured out a method to really do that. So it is, even in rocks that are highly deformed, it hangs out for a long time. It has a high closure temperature too. So that's similar to zircon. The hard thing about these minerals that we're trying to develop is we don't have good reference materials, or what some people call standards. So any data that comes into our instrument is wrong inherently because we have to deal with interferences and measuring other isotopes that interfere with what we're measuring. So we always measure what we call a reference material or a standard at the same time. So we can calculate or we can normalize our data from the unknown relative to the standard maximum current price. But we do have a material from Russia that's called SPG cassiterite that's about 1.5 billion years old that we use. So this is sort of a raw analysis, and we are normalizing it to a synthetic glass. And the age we get is 1.736 billion years old. And we know that's the wrong age. Okay? It's actually 1.5 something. So we know that, and we apply it to, I'm just going to skip over this part, but we apply it to what we call a correction factor. Okay, so the age we determine on the reference material, we know how far off that is from its actual age, and then we apply that correction factor to our unknowns. And so during this analysis, we got 1.718. We know the true age is 1.5, and we apply a correction factor to all the data that was run during that analytical session. So that's a correction factor approach that my colleague, Leonid Neymark, and myself developed in our lab. And so we tested this on as many cassiterite material as possible, or different ores, deposits. And we wanted to show that it was robust through time. So the sample on the left is 20 million years old, the sample on the right is 2 billion years old. Okay, this method seems to work regardless. So this is an example of all the different cassiterite analyses that we did through geologic time, just to show the robustness of it. And we know that these are generally correct because there are other ways that the ages of these deposits were determined. We've even done like district scale studies of the Cornwall region cassiterite, and it agrees well with previously analyzed igneous rocks associated with cassiterite. So time to get to the results. So the geochronology of these LCT and NYF pegmatites in Maine and New Hampshire. So going back to look at the map of the Appalachian pegmatite belt, we're going to zoom in the northern Appalachians. I already showed you this map, and I showed you these relationships. Again, there are multiple series that have been developed by previous researchers, and they did a really good job of putting them into different series. So the first series we looked at is called the Phillips series, and this is these are the results from the data. And so for those of you not familiar with geochronology, this is called a concordia. And that line, any point on that line is where two different isotope systems agree on the same age. So you want your data to fall. If your data does not fall on that line, your data is considered discordant. And when people are talking about discordant zircon, they would not use that data, be considered not good. In this case, the data, despite the fact that there's some discordant data, it sort of falls along the line. And basically, our interpretation is that it's a closed system, but that there's variable amounts of common lead in different grains of cassiterite. And in that case, you can put a line through your data, and where it intercepts the concordia, that is your age. Right? These are all corrected ages. As I was telling you, we need to correct for the fact that in situ methods never give you the right answer. And we're probably wrong anyway, but this is as precise and correct an age as we can get. The MSWD, it's just the mean, it basically tells you how much scatter there is. So you really want it to be about 1. But given the messy nature of these minerals, I'm okay with the MSWD of 3. It gives you an age about 346. This is data from the, that includes the pegmatites from that plumbago pegmatite occurrence. And these are slightly younger at 330 MA. This is another group of pegmatites that are yet even younger. So one thing to point out is that there are multiple pegmatite events in Western Maine. This is from, these are the NYF pegmatites from New Hampshire. The interesting thing about here is that that's Jurassic, they're Jurassic in age, okay? So they're much younger, but this big orange blob here is the White Mountain Magmatics suite, which is the same age as the cassiterite here. So these NYF pegmatites are clearly associated with the magmatic bodies in the area. So to summarize these interpreted ages, we recognize at least 4 pegmatite events. The Phillips series at 360 to 346, the Rumford series, which includes the Plumbago North, and the Oxford series, which includes the pretty famous or world famous Mount Micah pegmatite mines. And then finally, the Carroll County pegmatites. Again, this diagram on the right is a compilation of igneous ages in strigolzircon. But this is where our pegmatites fall in terms of age. They don't fall on these major igneous events, and they don't fall on what we think are major tectonic events in the area. We haven't been able to find a magma body with the same age as the associated pegmatites. And so this is not an occurrence that only happens here. There are other LCT pegmatite occurrences in Zimbabwe and Scotland where there isn't a known associated melt with that relates to these pegmatite bodies. And so the question is, what's going on? What drives the formation of these pegmatites? We don't think that's the case with the NYF pegmatites, but the LCT pegmatites seem to occur without associated magmatic bodies. And so what we do know is that these pegmatites, the LCT pegmatites, appear to follow tectonomagmatic events. And from a geodynamic perspective, what is happening post major tectonic events to give you enough heat fluids to drive pegmatite formation? That is something we're trying to figure out. So we don't know the parental magma granite bodies of the same age. And my hypothesis is that we just haven't found it yet. And the region is full of pegmatitic rocks, but a lot of the pegmatites have been dated and they're all older than the pegmatites. Okay. Another hypothesis, and I mentioned this earlier, is about this idea of having a salar located above and deep brine circulation of metal-enriched fluids. I don't know if you can actually drive circulation that deep, but you do need to enrich these rare metals somehow. This is a paper figure from Ian Hillenbrand in 2021, and it was leveraging some geophysical data, and they talked about an altiplano, sort of like the Nevada plano in the west, during and following the Acadian rock. And basically, what you see here is a difference in the depth to moho, and shown down here, they're calling it a moho step, which they're relating to a suture. But if you show where this Moho step is on the map to the right, there's possibly some correlation to this geologic feature. And there's, I guess, two things about this. One, you could have a high altiplano or a high altiplano, which resulted or persisted for at least 30 million years, give or take. And then you have collapse of the origin, which could drive heating and fluid mobilization. But that would happen after the main tectonic events. And then the other thing about the altiplano is that is the type of environment where you could potentially develop metal enriched brines. So that's Dwight's hypothesis. He really wants to get really great age constraints on these pegmatites so he could test that further. And so what we're showing here, and this is in this paper from 2019, is if we can get the age and their paleolatitude and put them in a place where you could form brine or enriched brines, which would be in the subtropical dry belt. If we could put those in context, both paleolatitudinally and by age, we could, you could further support this idea of a solar influenced process to these pegmatites. And so far, the ages, kind of work. They put them in subtropical dry belts during their formation. So is the solar hypothesis defensible? I think someone needs to model if you can move fluids like that. But it's kind of a cool idea. And so this is our modern resource of lithium in South America.